Leon Happ from the Technische University in Vienna. We'll talk about homogenization of non-local exchange energies in micromagnetics. Over to you.
Thank you very much for the nice introduction. I also want to thank the organizers, of course, for putting together this wonderful workshop, and especially to give me this opportunity to present my recent work here. All right, so maybe I should start with a clarification, because on the printed versions of the timetable you still find another title for this talk, but this ended up being work in progress, so I decided to present something which is finished rather, which I hope is still interesting for you, because it concerns also micromagnetics. And so, I mean, recently non-local energies in general, I would say, have come into fashion in studying problems or non-local versions of gradients, especially so convolution type energies, and we try to combine this non-local framework with a homogenization setup in micromagnetics, and see basically where this brings us. Okay, so very briefly, the outline is the following. I will recall the theory of micromagnetics, but just to get everybody on the same page. I mean, of course, you are very well acquainted with this, and we've seen it a couple of times. And then I will transition to the non-local version of the model that I will be concerned with afterwards. And then after having introduced this, I will also introduce the homogenization setup, give you the main theorem, the main result of our work, and then talk a bit about our methods and about a non-local version of two-scale convergence, which kind of can be nicely applied in our setup to yield the results we want. Okay, so let's fix some domain omega in R3. And of course, if you want to study the magnetic properties of a material which occupies this domain, then you're interested in this magnetization vector, which we have seen throughout the whole week, of course, which will be denoted here starting with a capital M. And so this is the vector field of the magnetic dipole moment of your material. And then there is this well-known saturation constraint. So when you're in a single crystal material, then underneath a certain temperature threshold known as this Curie temperature, your magnetization will have fixed strength, and this is this MS, this magnetization strength, which I introduce here. And then you can decompose your vector capital M as this factor times the direction vector of magnetization, which then lives in the sphere. And so this is what I will call also magnetization just from here on. Okay, and so then according to the theory of micromagnetics, which was recalled a couple of times already, dates back to the seminal works of Lano and Lipschitz, and then there have been contributions afterwards. The energy functional you want to consider consists of the following contributions. So you have exchange energy, the symmetric classical term in form of this Dirichlet energy. You have this DMI, which was discussed a couple of times, which is, of course, nowadays very prominent because it facilitates this emergence of skyrmions. And then you have anisotropy, magnetostatic energy, so this is the stray field, and the Seemann energy. Okay, I will not go further into detail here because we've heard about this a couple of times. And let me say also in perspective of what I will tell you later, that these three terms, their homogenization has been studied already, and you can see that they constitute gamma continuous perturbations of the model, so I will really concentrate on those two terms here in the following, and on non-local expressions of those. Okay, so this is posed over the Sobolev space H1 with values, where the functions have values almost everywhere in the sphere. And regarding the coefficients, we want that A is strictly positive, just for coercivity reasons, of course. Kappa is the DMI parameter, which can take arbitrary values, and these are the Jelasinski vectors. Okay. So to introduce the non-local model, I want to take a step back historically and go to Heisenberg, to his contributions from 1928, which were actually very important in developing this theory later by Lano and Lipschitz. And so this was one of the first variational approaches really to this problem of micromagnetics and explaining the domain structures. And so he proposed this atomic model actually of atomic spin interactions. So you have a lattice, which is this capital lambda here, and you have these atoms with spins mi and mj sitting at the different lattice sites, and they interact via the scalar product, and then you have this symmetric tensor here. which governs the interaction. You have some spin magnitude here. And so later this was extended to also encompass antisymmetric exchange energy in the fashion of the Jelosia-Morinsky interaction in this form here. So you actually have antisymmetric terms of this cross product, and you have these antisymmetric Jelosinski vectors here. Okay. And so if you look at this model, you can come up with a continuum version of this, which has the following form now. So you replace these local gradient expressions. I mean, okay, not in that, they weren't gradient expressions yet, but I'll come to that in a second. But you express these local expressions, these non-local discrete expressions here by a continuum approach, where you weigh them via the convolution with these kernels, rho delta and the nu delta here. And the delta you can imagine is some interaction horizon basically that you have in your model.
What is the dimension of omega?
3. So this is 3-dimensional, yes. And okay, so what you want, I mean, and then it's tempting to study the localization behavior. So you let the interaction range delta go to 0, and what you want is, of course, you want to recover the local model that I introduced at the very start. And I will concentrate from here on now on kernels which are obtained by rescaling fixed kernels rho and nu in the usual fashion. And so you have automatically always this localization condition fulfilled. So if you look, which is very important if you work in this kind of field, right? So if you look on balls outside a fixed radius and you let your horizon go to 0, then the mass outside these balls will always vanish in a limit. So you really have this concentration property. And so due to this setup, this is always a given now in the following. Okay, and then, as I said, you want to study this localization behavior. And okay, you don't have to look at this in detail. These are just conditions that you then put on the kernels that need to be fulfilled. Usually you want them to be integrable, unit norm, and non-negative, and then if they are radial, basically you don't need anything more because we have this localization property. If they are non-radial, you want to compensate for possible degeneracies and so on. And so you need to put some conditions, and here also, because you have these two kernels, you want some compatibility between both of them. Okay, and then in a recent contribution from Rossella, who is one of the co-authors also of this paper, and Giovanni and Elisa Davoli, from TU Wien also, they showed this result. So they studied the gamma convergence behavior in the localization limit. And so what they showed is if you take a bounded Lipschitz domain in R3, you assume the contributions from the last slide, the assumptions from the last slide, then there exists a finite radon measure which has unit norm on the sphere, such that up to taking a subsequence, these non-local energies actually gamma converge in the L2 topology to this functional defined here. And this exactly reflects already the antisymmetric exchange we have seen. And this is kind of an anisotropic version of the exchange energy, which is inherited from possibly non-radial kernels. If you take radial kernels, you get exactly up to multiple the symmetric exchange energy from before. Okay, and so this is the starting point actually of our analysis then, because we are intrigued by this question, okay, what happens if you put this into a homogenization framework? And kind of how do these non-local energies carry through to the effective limit? And so maybe to give you an idea about this homogenization, I mean, in general, you can think about this as follows. You have some body omega, right? And you have some, for example, some inclusions. Here it's only two materials, but we only assume periodicity. So, I mean, this can also be like many components basically of a composite material, something like this. The important thing is we are in the periodic framework here, so you have some scale epsilon, and on this scale, your materials oscillate. Okay, and so the multi-scale problem we have then, because we have two scales, we have the scale of the non-localities and the scale of the homogenizations, of the heterogeneities, has the following form. This is this G epsilon delta, and we have the symmetric contribution and the antisymmetric contribution. And we have these parameters A and kappa, which are oscillating now. And so we assume they are in L infinity and periodic. This hashtag subscript denotes the periodicity. Okay, and so the question in homogenization is then, what is the variational behavior? if we assume a coupling between both scalings, right? So the interaction horizon should depend also on this epsilon. And if you let epsilon go to 0, what is the limit model you will cover? Okay, of course there are different scaling regimes that you can study. So the first one would be that the interaction horizon goes quicker to 0 than the scale of the oscillations. The second one is that they are comparable, and the third one is that basically first your heterogeneities, the scale goes to 0, and then you localize afterwards. And so I guess this first one is probably kind of the one you can the easiest see what happens, because here you would first localize and then homogenize. So you would expect that basically you get the effective limit for the local exchange energies. This is nothing we have thoroughly studied actually, so I mean, don't take my words too exact here now, but I guess this is what you could get. We were more actually intrigued by the second case of these comparable scales, where you assume that they tend to some value which is finite. And I mean, this is, I think, the toughest regime, because you first kind of let your scale of the oscillations go to 0, and then you homogenize, so it's not exactly clear what will happen here. But so we first set out to study this case, and now in the future we want to also understand what happens in this regime. Okay, and so now to the hypothesis that we assume. Okay, for the coefficients, I already told you we want them to lie in L-infinity periodic here. Some lower bound for the exchange to get coercivity. The kernels should be integrable, non-negative, L1 like unit mass, and because we don't assume radiality, right? We also need something to assure the non-degeneracy of our kernels, and kind of basically this is our assumption here. And for this antisymmetric kernel nu, we want similar things, so also L1 unit norm. And I remarked that we don't assume it from the get-go to be antisymmetric, but you can always decompose this in its symmetric and antisymmetric part. And the symmetric part, if you pair it with the cross product in the integral, which is antisymmetric, of course, will cancel out. So you could also, without out of generality, assume that this is already antisymmetric, but it's not important for our analysis. And for the interaction, we assume that kind of this fraction here is bounded in L2, because it pops up throughout the calculation, so you need some control over it. Okay, and so I remark finally that these hypotheses are, not far from being optimal, but we don't know if they're optimal. So for us, they were sufficient, and also they deviate already a bit from the localization result that I presented before. In recent years, there have been some investigations into optimal conditions for these localization results in the spirit of the works by Vogel, Precis, Mironescu, and Ponce afterwards on gamma convergence for these convolution type energies. One paper is, for example, by Elisa, Giovanni, and Valerio, and since then there have been also other contributions. But so I don't claim optimality here, but these are just some sufficient conditions, which are still fairly general, I think. And so, okay, so in order to formulate now our final result, here's the notation. Okay, the functionals we consider are this G epsilon, where the delta also depends on epsilon, symmetric part, antisymmetric part. And then regarding the homogenized density, we need these kernels rho lambda, which are just the lambda rescalings of our rho, nu lambda, which is the same. And I remind you, this lambda is the limit of the fraction of the delta epsilon over the epsilon. And then we define this density here. Okay, I will come a bit more onto the peculiarities of this density on the next slide, but just to give you the result here now, I guess this is already what you may expect it. So take omega, a bounded Lipschitz domain, we assume the assumptions from the slide before, and then our sequence, which you can find up here, gamma converges with respect to the L2 topology to this effective functional here, which we just extend to the whole space L2 by setting an infinity outside of H1. Okay, and this is also complemented with a compactness result which goes with it, of course. but I'll come to that at a later point. Okay, so let me now maybe point out what is special about these, the homogenized limit. So first of all, it comes in the form of a cell formula. So this is what you would expect for convex energies when you homogenize them. I mean, in general, the problem itself is non-convex due to the sphere constraint, right? But still, since the density itself is convex, you get a cell formula in the limit. And you can compare it with the result of Elisa and Giovanni a couple of years ago, where they studied the homogenization really of the purely local energy. And so what you get is this expression here. So you take the infimum over H1 functions, which are periodic, and this 0 denotes that they have 0 average value on the cube. Because normally this is only defined up to a constant, and then you can gauge it basically by doing this. And so these are the functions taking values only in the tangent bundle, and then you have these expressions here. Okay, so what is the difference now in our case? Okay, we also have this tangent bundle constraint here, which is of course inherited from your sphere constraint of the original problem. I mean, this is well known. And then additionally, we have really a non-local formula for what is here in the brackets. And so you can see that basically really what we do is the joint localization and homogenization. And so the localization now reflects on the scale of this effective limit here. And yeah, I mean, this is really just basically non-local analogs of these expressions here. So I think this is quite interesting to see. And so, okay, from here on, to make the notation a bit lighter, I will just set delta epsilon to epsilon. So in particular, this lambda will be 1. And okay, I just recall now the notation. So I dropped the epsilon, and basically the rest is the same. And here I dropped the lambda because it's just 1. Okay, but all results I will present, of course, hold also for this more general case of the comparable scales. Okay, and then we also have a characterization of these minimizers. So let's take now some tuple SA in this tangent bundle here. Then the unique minimizer of this cell formula, or of this density here, is given by this expression, where VA and V kappa can be obtained by minimizing these strictly convex energies. So this is where you get the uniqueness. And these are basically the two parts of the, so coming from the symmetric and anti-symmetric part of the functionals. But you don't have to look at this in detail here. It's just to tell you, so you have some kind of explicit minimizer here. And so you can reformulate your homogenized energy density here in the following form. And you have some average quantities basically. And so the interesting thing now to see is that the first 2 terms here, you can calculate directly that basically they are the same, similar to the energies that were obtained in the localization result. If you look at these kernels basically, which are the averaged versions that you can see here. And so in addition to these 2 terms, of course, you have this third one, which is purely negative, right? And so kind of this can be seen as somehow the pointwise limit of your homogenization here. And this kind of additionally lowers your energy in the gamma convergence result. So this is really kind of the localization, the pointwise localization in some sense, and this really comes from the additional homogenization effect. Okay, so this is just, I think, a nice observation here. Maybe now some quick words about what is the state of the art regarding such problems. Of course, convex homogenization goes back to the important contribution from Marcellini from 1978, and then later Alea kind of using 2-scale convergence was able to prove or to provide a different proof of the homogenization for convex energy densities. And okay, a modern account can be found in the book by Paredes and De Franceschi on homogenization. The main, I mean, what is important for us here is that this use of the two-scale convergence method, right? Because this is, especially for convex densities, this is very well suited to very elegantly, in a very constructive way, perform the homogenization. Whereas Breides, in his book and also in his results, mostly uses this more abstract localization techniques, which finally goes back to ideas of Dedorji and you use this fundamental lemma. And so this is a bit more, let's say, implicit, whereas the two-scale convergence approach is really very direct. And so our idea was really to apply this also to this non-local setting. And this is what I will present afterwards now. And so in general, about the homogenization in micromagnetics, there were these contributions by François Alous and Giovanni, where they homogenized the local full micromagnetic energy, basically, but without the DMI. The DMI was later included in this work, which I already told you about of Giovanni and Elisa. And then there's also this contribution here about homogenization with manifold constraints. So they already deduced that you will in general have this cell formula where you have this tangent bundle constraint over the functions that you minimize. Okay, and then there were additional contributions. And non-local homogenization, interestingly, is a very new field. So actually the first real papers I'm aware of are from the start of the 20s now, by Breides and Piernitsky, where they study also the stochastic homogenization of convolution type energies. And a couple of years ago there appeared a monograph of these authors on this topic. And this was actually a starting point also of our analysis. So we stumbled across this book basically, and we thought, okay, what can we do in our setting with their results? And also here they don't use two-scale convergence. So the idea was okay, maybe we can devise a general tool kind of to tackle convex non-local homogenization problems. And it all fell into place neatly, I would say. Okay, so with this, I come now exactly to two-scale convergence. Maybe a reminder of, for those who are not well acquainted with this topic, first introduced by Nguyen Tseng in 1989, and then there's this famous paper by Allaire a bit later. And so, okay, let's fix some Mn natural numbers. E should be an open subset of Rn. We denote by eta the variable living on the space E. We attach to every point in E basically a cube, denoted by Q eta, and the variable living on this cube is denoted by zeta. And then the main insight of two-scale convergence is that for bounded sequences in L2, you have compactness in the following sense. So take a sequence in L2, and we say that a two-scale converges to a limit, which now has this additional variable, which is also called a micro variable. And the variable here is the macro variable or fast and slow variable. There are different denotations. And so we say that this converges to the limit function if these integrals, where you pair it with a test function which has to have a certain amount of regularity that this works. So you take a test function which has a pure oscillation in the second variable. And then you require that the limit takes the following form. So we have the double integral over E and then over the cube. Okay. So if you first see this is a bit strange, I would say, because somehow out of nothing there emerges this additional micro variable. And so kind of the idea, how I like to think about it, is that this function here acts like a filter in some sense. So I don't know, maybe there's some similarity to polarization filters or something. So this dictates kind of the oscillations that you have, and it picks out the oscillations in your sequence V epsilon, which are in synchronicity basically with these oscillations here. And this is kind of the limit function that you get here in the double integral then later. And so this is weak two-scale convergence denoted by this double hookup arrow here, and strong two-scale convergence means that you have additionally convergence of the norms. So this is kind of in the spirit of this Radan-Ritz property of uniformly convex planar spaces. Okay, so maybe to another way to see this is from the angle of compensated compactness. So there's a quote of Tatar in his first major contribution to compensated compactness, where he says plainly there are some nonlinear functions which are nicely behaved with respect to weak convergence. Okay, and this is exactly one very nice example of this. So you take the purely oscillating functions basically, and you can make sense of this in this spirit of compensated compactness if you look at the Young measures of these kind of functions here. Okay, where this is just a product of some function with some pure oscillations, and and you pair it with some function v epsilon here, and you look at the limit. And then, if you look at the Young measures, there are some works on this. There's also called two-scale Young measures, and you kind of get to the same results here. This is just a remark to maybe put this in the right light. Okay, and then we need some notion of, we call it x2-scale convergence, because ultimately we'll have two variables. We'll have the space variable, and we have like the interaction variable. And so we needed something, we really needed a notation for functions where you only have oscillations in the space variable. So we add this x to the notation, and we split our domain as a product now, ex cross xi, and you will see in a second why this makes sense, right? And then we only consider oscillations in this x variable. But the rest is the same, and the notation is we just put the x above the arrows. Okay. What are the important properties of two-scale convergence, and then also this x2-scale convergence? The most important one I already mentioned, this is this compactness property. So each bounded sequence admits a subsequence which weakly x2-scale converges to some limit. This is very important. You have the lower semi-continuity of the norm with respect to the weak two-scale convergence, which is of course a very good property that you can exploit. You have convergence of products. So if you have a weakly and a strongly two-scale convergence sequence, you put them in the integral, you can pass to the limit, which is then basically just the product of the limits. And you have further properties which you kind of used from usual weak and strong convergence in LP spaces. And this is no surprise actually, because there's a way which is called unfolding operator to really translate two-scale convergence in convergence basically in this product space E cross Q, right? And there you have all these nice properties for LP convergence, and they really translate also to two-scale convergence. But yeah, this is of course very well behaved. So this convergence, and you also have this density result. So in order to show two-scale convergence, it suffices to do it for a dense subset of your space. Okay. So let's come back to our functions now. Let's concentrate for a second on the symmetric part, which is this F epsilon energy. I introduce this new variable xi, and if I do the change, so transformation to this variable, what we get is this expression here, where now this xi is really the difference between the 2 points, and this x is the old space variable, and here we have to constrain ourselves to a subspace of this omega. This is just defined in a way that this sum lies in your original space omega. So this is just to make it well defined. And then you see already that maybe it makes sense to study the two-scale behavior of this property. Okay, so which is basically just the square root of this quantity. Okay, together with the indicator function of this one. Okay, and this will be denoted by this delta rho epsilon. So this is this difference quotient here. Okay, and of course, you can already see if you do basically the analog of partial integration in this framework, you will get kind of as a dual operator this expression here. Okay, and so the main kind of result, setting up then the gamma convergence result in our paper is this here. So we assume this hypothesis on the coefficients and on the symmetric exchange energy, symmetric kernel, sorry, and we take a sequence which is bounded in energy, and then there exists a limit m0 which lies in h1, So through this localization property, you basically gain regularity, and you have an additional function W, which is in this space L2 omega into L2 periodic vanishing mean value on the cube, such that up to a subsequence, okay, this one converges really in L2, and so this will be your limit function. But additionally, if you concentrate on the two-scale convergence of this sequence, then this is the limit, where you have here the gradient of M0, and here you have a non-local expression, so the difference quotient basically, or, no, this is not a difference quotient anymore, but yeah, it's kind of a non-local expression. And I'll come in a second to a comparison with the local case here, but let me just add that if additionally you know that the sequence you started with only takes values in the sphere, then this carries also through to your limit. All right, so okay, the compactness can basically be obtained as in the paper by Ponce, where he studies the gamma convergence of such non-local functionals. I mean, what you need to observe, and this is exactly as in the local case, that you have bounds of the anti-symmetric term in terms of the symmetric energy. And so if you have a sequence which is uniformly bounded in energy, then you easily get that basically the symmetric exchange is also uniformly bounded. Then we need this additional property on our kernels, that they are kind of this non-degeneracy property, and you can find that kind of this expression is uniformly bounded, where this rho epsilon tilde now basically, I mean, okay, it's defined here, but the important thing is this meets exactly the assumptions in this Ponce result, and so then you get the first compactness here, which I was giving you basically for free. Okay, but this is really the important part for us. Okay, so what happens here? So the local analog of this you can find in this is proposition 1.14, I think, in this paper by Allaire. This is super important. So if you take a bounded sequence in H1, which converges weakly to some limit, then you already know that your sequence converges weakly to scale to the same limit. But additionally, there exists this V, L2 omega into H1 periodic vanishing mean value, such that up to a subsequence, if you look at the gradients, then they weakly two-scale converge to this expression here. I mean, maybe to give you an idea why this kind of makes sense, is the prototypical functions you maybe should have in mind are of the form, in this case, u0 of x plus epsilon v of x over epsilon. So if you take the gradient here, you immediately see that this holds true, because the gradient, the x variable in the first one, will be damped out by this epsilon. And if you take the gradient here, then these epsilons cancel out. And so you see kind of the z gradient of this contribution in the limit. But this holds in general, right, for bounded sequences in H1, not only for those. Okay, and so the idea was to just mimic this result in the non-local case. And here, if you look at the proof, it goes like follows. Okay, you just take smooth functions, basically. The rest can be done by density. Okay, so you need to look at this expression. You partially integrate here. And you get two contributions. This one is fine. Here you can pass to the limit just by the two-scale convergence you get here, because u epsilon goes to u0. And this is smooth, so it behaves nicely. So for this first integral, you can do all the calculations, and you end up here. So this is then the gradient u0 you see here. But this only works, of course, if this is 0, right? And this is, in general, kind of a problematic term, because you have no control here. This can blow up if epsilon goes to 0. But so if you denote now, or if you take now, I mean, by compactness, you already know that this has a weak two-scale limit. You look at this limit, and so you know that it agrees on the kernel of this divergence operator, that it agrees with the u0. And so then you can just apply the Helmholtz decomposition, and then you know that the full limit is given by this expression, plus something, plus something which lies in the complement of the kernel of the divergence operator, and these are the curl-free fields, and so this is given just by a gradient here. And of course, this is just well-defined up to a constant, but if you take this gauge, basically, then it's fixed. Okay, and so you want to repeat this now in a non-local case. I mean, for simplicity, again, we assume that those functions are already sufficiently smooth, and also that your kernel has compact support. Otherwise, you can exhaust basically your whole R3 by taking larger and larger radii. But these are just technicalities. And then again, we need to study the limit behavior of these kind of products, where, okay, we can now, so I mean, you can shift this difference quotient to this side, you get this expression, and then you add and subtract this term here. And so now the first one looks basically like a difference quotient here in the first variable. I mean, up to this epsilon you have here, but you can treat them nicely because psi is again smooth. So again, you know what happens with this term, and this is the problematic one. And so this one you want to set 0, right? Because this can actually blow up. And so again, you concentrate, okay, so you will concentrate on functions for which, okay, I have to go back, sorry, for which this expression is 0. And so to make this formal, basically, we define this operator as rho, which maps from its domain into this space here, and it's given by this expression. And then you observe that the adjoint operator is exactly given like this. And if we go back, this is just what we have seen here, applied to the psi. And furthermore, you find that this is a densely defined, possibly unbounded, but linear operator with closed range. And so in particular, what you can deduce from this is that the kernel of this, so that the orthogonal complement of the kernel of this adjoint operator is just the range of this first operator. And so this is kind of the important ingredient just to make this argument now work. So, okay, we just take functions for which this adjoint operator is 0, then you can pass to the integral in the rest, you get exactly this gradient m0 here again, and then just argue in parallel to before, you use that the orthogonal of this one here is just the range of your S rho, and so you get that, if you denote by V the limit that you get by compactness, that you know that the difference between this and the pure gradient is just given by a function in the range here, and this is this expression. And so this is exactly what I claimed, and then you have to argue by density, and so on and so forth. But okay, so this is how you get this non-local analog. Okay, and this is for the third part. I will skip this now, that kind of this sphere constraint carries through. Okay, and so equipped with this result, you can then approach the proof of the main theorem. I remind you that this is what we wanted to prove. And so the remaining steps, of course, are now the lim infinite inequality and the lim super inequality. And just to make this a bit quicker now, let me say that this can be actually pretty easily deduced now just by elementary properties of this two-scale convergence, namely the lower semi-continuity of the norm with respect to the two-scale convergence, modulo some details, but this is basically what you use. And maybe let me go now directly also to the lim super inequality. So I skipped this part of the lower bound. And for this upper bound, okay, we need some auxiliary results also, just to argue by density. So if you want to make this rigorous, you define, we defined this norm with respect to this rho, which is given by this expression. You can show that it's a Hilbert space, and you can show that actually this space here is dense with respect to this norm. And so that the arguments in the following can be reduced by just taking functions in this space here. Okay, and this is now the last result also. This is how an approximate recovery sequence for us will look. So take your M0 in H1, and we take an arbitrary smooth function phi, which takes values here in the tangent space, and then you define these m epsilon of phi's. So to your M0, you add basically just small oscillations. I mean, in the spirit, as I've showed you here already, oscillations which are damped. And so then you can show that this sequence strongly x2 scale converges to this limit. And I mean, this kind of recovery sequences are very well known, let's say, in homogenization theory. This is always what you kind of used to do because, I mean, this is exactly your prototypical oscillations that you have, basically. So this is you could already like guess that this could be an idea. You only have to project it back onto the sphere, of course, to preserve your sphere constraint. And then here you have to really be careful kind of to make everything work. So it's not maybe as easy as it might seem. But yeah, you can show that this holds true. And then if you use this density result above, so if you compare this now, I mean, if you plug it in into your functional, you compare it with what you want to get out, then you basically just need to approximate some quantities with these phi. But due to this density result, I've shown you this all works out kind of, but as in the usual cases. So if you're acquainted with homogenization, this is really no problem from here. And so this finishes the proof. Maybe a small summary. So we have discussed now this joint localization and homogenization of this non-local model in micromagnetics with this additional manifold constraint, which is inherited from the model. And so this is really something which was not considered before, even though you see that it really doesn't add much difficulty to the problem. But you can see it nicely reflected in the limit. And in particular, we've studied this non-local two-scale gradient decomposition as an extension of the local result. And so I think this is something which can also be transferred to study other non-local homogenization problems in the future. And of course, further directions are for us to really rigorously explore also these different scaling regimes to get a full picture of the multi-scale problem. Okay, so these are the two references mainly which I've discussed. So this is this localization, a gamma convergence result, and this is our recent preprint. Okay, and with this I finish, and I thank you for your attention.
Thank you, Leon. Questions? John?
So what's the status of these non-local models in magnetism? Are the situations where we know better predictions than local ones?
I don't know if we are that far already, I have to say. I mean, these non-local energies really were first studied, I think, like thoroughly by Bouguin, Precis, Mironesco, but they were taking this from a purely functional analytic point of view, basically. So they were not thinking about, not in the first place, maybe about applications, and then, I mean, Pons extended these results also to gamma convergence results and so on. And then I think the main applications where they are considered is in what is called peridynamics. So dynamic models where you have interaction horizons between particles. But I mean, in this framework, it's kind of natural, right, to consider this because on the discrete level of the atoms, you also have some non-locality, of course. But I mean, this is a good question actually in the end. What is the predictive power of these models and so on? But I think this has not been really compared to the local case here.
Other questions? Yes, Philip.
So in magnetic crystals, it is well known that we can approximate exchange interactions with functions like exponent times sine, or maybe some power law times sine, which is more sophisticated. And of course, it's very nice if we can get rid of double integral with using some rigorous arguments and to transform it to some local expressions plus maybe something else. And it is clear that first accounting for these non-localities will renormalize usual constant. So exchange stiffness, Delachinsky-Mori interaction, and of course we can account for this easily. So it probably was a bit complicated for me to distinguish what we can immediately use from your theory to simplify our studies. So I mean, what kind of term extra the conventional one we can write, which is less complicated than double integral. So
I mean, I think this is a very good question. This is probably something we would need to discuss more because this, I mean, for now, because for now this is really just a purely, like, let's say, mathematical result, right?
I can answer.
Okay, yeah, perfect.
So in some sense, the classical theory of micromagnetism is always in H1, and it's a first order approximation of theory of that sum that he was writing about Heisenberg sums. And if you work directly with this non-local model, which are the natural generalization of these Heisenberg sums, like when you study electromagnetism, you you start with a discrete sum of charges, and then from this you pass from one measure to the Lebesgue measure, and you immediately get this non-local expression. So as soon as you work with this non-local energy, all your macromagnetic theory just works in L2. So you don't have any more to use these H1 spaces. And these H1 spaces are actually just a result of this approximation that you are doing, the approximation of very short range interaction only. But if you want intuitively a more general energy function, this should be the energy function that you should consider in some sense. So,
but it is more complicated.
Yeah, it's more complicated. But this, for example, I'm talking with physicists that working on quantum field theory. They say that these boundary condition that using micromagnetics, like dn of m equal to 0, this is just a result of the fact that you're doing a first-order approximation, because you approximate something which is non-local with something local by forgetting about long-range interaction. So just taking very short-range interaction, you get this gradient, and then when you write the Lagrange equation, this being 0, the normal component of magnetization is just a result of your approximation. It's not something that is in the real model. And they say that actually this kind of boundary condition is not something that you can explain from let's say foundational or very primitive result of physics. So
okay.
I think that the point is that with this model you can hope for to see phenomena that you cannot, or explain phenomena that you can see experimentally, but you cannot see from the classical theory of magnetics.
I think there's probably more to discuss, but I'll postpone that to lunch at Churchill, in fairness to the last speaker. So let's thank Leon again for a beautiful presentation.